Hi, this is the video for section 5.1 of A Student's Guide to the Schrödinger Equation. This is the first of three sections that deal with specific potentials. In this case, it's the infinite rectangular potential well. This whole first page describes the well. It's helpful to look at this picture as you're considering that description. It's a configuration in which the potential energy is infinite on two sides of what's called the potential well. Within the well, the potential energy is zero. These are called rigid walls because the force at each of these locations, x equals 0 and x equal a, is infinite and directed inward at the left wall and inward at the right wall. So the discussion on this first page just points out that this is not physically realizable since you don't have infinite forces in nature. But this does turn out to be a very instructive configuration, and it's actually a useful approximation for several real-world problems. This paragraph reminds you of the connection between force and potential energy. Specifically, force is the negative gradient of the potential energy. You can read about the gradient back in chapter 3 if you haven't already. But since the potential energy changes from infinite to zero at each edge of the well, that means that the forces are infinite there. Also, since there's no change in the potential energy inside the wall, that means there's no force on the particle inside the well. Here's the mathematical statement of the potential energy being infinite outside the well, considered to extend from x equals 0 to x equals a, and zero potential energy inside. This just talks about the directions of the forces always being inward, and that means the particle is trapped by infinitely strong inward-pointing forces at both walls. A little footnote about why this is sometimes called a square well. This paragraph does point out two unrealistic aspects of this configuration. First of all, you cannot really have infinite potential energy outside the wall, nor can you have an infinite slope of potential energy at the walls. But what we're going to do is solve the Schrödinger equation inside the well and then solve it again outside the well and join those solutions together at the boundaries of the well. And as it says here, it's a good pedagogical example. You can learn a lot from this, and some of the techniques you learn here you can apply to more realistic configurations, such as electrons trapped in a strong electrostatic field. So if we want to know how the particle behaves in such a well, we need to find out what are the possible wave functions for a particle in the well. And what does possible mean? For one thing, it has to satisfy the Schrödinger equation, but it also must satisfy the boundary conditions at the edges of the well. Now, with infinitely sloped walls, we cannot make the slope continuous across the boundaries, but we will insist that the wave function is continuous, and as I said, we're going to solve the Schrödinger equation both within and outside the well, and then match those together. So we're going to use separation of variables. That is, we're going to divide up the wave function psi of x and t into psi of x and t of t. If you work through section 4.3, this is what the Schrödinger equation looks like in that case, where E is the separation constant we use to separate the temporal and spatial equations. And this is a reminder that it's the solutions of the time-independent Schrödinger equation that are the eigenfunctions of the Hamiltonian or total energy operator. And the eigenvalues associated with those eigenfunctions are the possible measurement outcomes. And that's what we want to know. Also back in section 4.3, we talked about the case where the total energy is greater than the potential energy. If that's true, you can write the time-independent Schrödinger equation like this. And remember, we took these constants, called them k squared. That makes k equal to this value. But remember, we're going to take inside the well v equals 0. So in fact, we have our k proportional to the square root of energy. We also found that the general solution looks like the sum of these two exponential functions. In areas in which the potential energy is greater than the total energy E, we write the time-independent Schrödinger equation like this. And you recall, we gathered up these terms and called them kappa squared. That makes kappa equal to this, with a general solution that looks like this. Once again, remember, these exponentials have real exponents. There's no I in there to make these oscillate. So what do we know about C and D? Well, we know the potential energy is infinite outside the well. So that makes the constant kappa infinitely large. You can tell that from here. When V is infinity, kappa is also infinity. So what does that mean? Well, if this is infinitely large, this term's going to blow up at any positive x. So c must be 0. But at negative x, this term is going to be infinitely large when kappa is infinite. So that means d must also be 0. And if c and d are both 0, the wave functions must be 0 everywhere outside the well. And the probability density is equal to the square magnitude of the wave function. That means you have 0 probability of measuring the position of the particle to be outside the infinite rectangular well. In the next section, we're going to deal with a finite rectangular well, and that will not be true. But in this case of the infinite rectangular potential well, the probability density is 0 outside the well. Okay, let's go back to inside the well and see what happens at the boundaries. That is x equals 0 and x equals a. Here's psi of 0. Just plug in 0 for x there and there. We know that that wave function must be 0 to match up with the wave function outside the well. That means that a plus b must be 0, or a must equal minus b. Combine that with the boundary condition at the right wall, where we plug in a for the value of position in these two terms. Notice that we've put in minus a for b, set that equal to 0, and we get this expression. If you look at this one, you say, but isn't it possible that a is 0? Yes, but if we set a 0, since we know that a equals minus b, that would mean b is 0, and we would have no wave function at all. So a can't be 0. That means this term must be 0. And to understand that term, use that inverse Euler relation. You saw that previously in chapter 4. That relates sine of theta to this difference between exponentials. And that means our expression looks like 2i times sine of ka, and that must be equal to 0. So how can that be true? We know 2i is not 0. That must mean that this sine function is 0. And where does the sine function equal 0? Well, sine of ka would equal 0 if ka equals 0. Or ka could be an integer multiple of pi. Because remember how a sine function looks. Here's sine of theta, here's theta, and at pi, and at 2 pi, and at 3 pi, and at 4 pi, the sine function is 0. So we can call that n pi, where n is an integer. But I first deal with the case that if ka equals 0, that would mean that k must be 0, because we know a, the width of the well, is not 0. And if we set k equal to 0, then the separation constant e, the square root of which is proportional to k, must also be 0. And what does it mean if e is 0? Look back to our expression of the time-independent Schrödinger equation. Here's the curvature of the wave function, the second spatial derivative. Here's k squared. If we're going to allow k to be 0, then the curvature must be 0. And we said that the wave function is 0 at the edges of the well, so if it has no curvature, it must also be 0 inside the well. So ka equals 0 is not a good option. And that means ka must equal n pi. And if ka equals n pi, we can solve for k. I've added a little subscript n here to remind you that n takes on discrete values. So k sub n must equal n pi over a. That's already a very significant result, because it says that the wave numbers k sub n within the infinite rectangular well are quantized. That is, they have a discrete set of possible values. This all comes about because the wave function must have 0 amplitude at the edges of the well. And since the wave numbers are quantized, that means the energy is quantized. If we solve that equation relating energy and wave number for energy, we get this. Look at these values. You can have n equals 1, or n equals 2, or n equals 3, and that's going to give you the allowed energy levels. So we haven't yet talked about the details of the wave function, or how it evolves, or the probability density, and we already have a fundamental result that inside an infinite potential well, quantum particle can take on only certain energies. And even the lowest energy state at n equals 1 has non-zero energy. Some people call that the 0-point energy. Now, one thing to be careful about. With these quantized wave numbers k sub n, some students want to say, ooh, that means that momentum is also quantized, because p is equal to h bar k. But that's not true. As we're going to see later in this section, momentum can take on a continuous set of values within an infinite potential well. And to understand why that's true, remember, if you make an energy measurement of a quantum particle, its wave function is going to collapse to an energy eigenfunction. If you then make a momentum measurement, the wave function collapses to an eigenfunction of the momentum operator. And the eigenfunctions of total energy and momentum are not the same. So you cannot predict your momentum outcomes using the energy you found in the first measurement, because the particle changes state when you then measure the momentum. As I said, we'll see later what the momentum probability density inside the well looks like. In general, it'll be a continuous function rather than discrete values such as k sub n has. But if you let n grow very large, the probability density will be greatest near the momentum values that are h bar k sub n. Okay, the next thing to do is to take our values for k sub n and plug them into the time-independent Schrödinger equation. Here they are, here and here. Another way of writing this is with a prime. Remember, there was a 2i factor. I've absorbed that into the a to make it a prime. And this is what our wave functions are going to look like. They're going to look like sine functions. Before we see those, let's normalize them to see what that a prime is. To normalize, you set the integral of psi star psi over all space equal to 1. We plug in psi star. We plug in psi. That gives us this integral. A prime is a constant, so it's going to come out of the integral. Here's an integral identity for sine squared. When you use that, plug in these values, you get that a prime is the square root of 2 over a. When you get that from this expression, you may say, wait a minute, shouldn't this be plus or minus the square root of 2 over a? Well, it points out here, minus a prime can be written as a prime e to the I pi, because e to the I pi is minus 1. But a factor such as e to the I pi in a wave function is called a global phase factor. It affects only the phase, not the amplitude of the wave function. And since global phase factors apply to each of the component waveforms that make up psi of x, they have no effect on the probability because they disappear when you take psi star psi. So if we just take the positive root, we're not losing any information. That's also why we said n was a positive integer in the wave function. With the square root of 2 over a for our constant, here are our wave functions. And you can see those for n equals 1, 2, 3, 4, and 20 in this figure. You can see the shapes of the waveforms in here, starting with the ground state waveform. That's n equal 1. You can see the n numbers on this side. You can see the energy values on this side. And notice that each of these has a node that is an amplitude of 0 at the wall. It has to, because it has to match up with the 0 amplitude wave function everywhere outside the infinite potential well. Notice also that the lowest energy, that is the ground state wave function, has a half cycle. That means there are no nodes within the well, just the 2 nodes at the edges. But as you increase to higher values of n, that is, to higher energy wave functions, you add 1 node each step you go up in n. So n equal 1 has 0 nodes within the well, n equal 2 has 1, n equal 3 has 2, and so on. By the way, notice that since we call n equal 1 the ground state, that means that the first excited state is called n equal 2, the second excited state is called n equal 3, and so on. You should also notice the symmetry of these. That's better shown on the next figure, where I've put a dashed line down the middle. And in some quantum texts, you'll see that called x equals 0, so the potential well will extend from minus a over 2 to a over 2. Still has width a. The reason for showing it this way is that you can see that the n equal 1, that is the ground state waveform, has even symmetry. That is, if you go a distance to the left and a distance to the right, you get the same value. That's also true for n equal 3 and for all wave functions with an odd value for n. But for the even values of n, notice what happens. If I go a certain distance left, a certain distance right, the wave function has opposite sign. That's called odd symmetry. But as long as the potential energy is symmetric about some point, which it certainly is about the x equals 0 point, since it's 0 on both sides of it, then each allowed wave function will have either even or odd symmetry. As it points out in the text, there are a lot of functions which have neither even nor odd symmetry, so it's very helpful to know that when you have a symmetric potential energy function about some point, the allowed wave functions will have either even or odd symmetry. That's going to be especially helpful in the next section when we talk about finite rectangular wells. One other point to notice is that even though we tend to draw the spacing between these different wave functions as uniform, in fact, the energy difference between the ground state energy and the first excited state is smaller than the energy difference between the first excited state and the second excited state. In other words, the farther up you go, not only are energies getting bigger, the energy level difference is getting bigger. That's because of that n squared in the energy term. So this has a 2 squared in it, which is 4. This has a 1 squared in it, so that's 1, and the difference therefore has a 3 coefficient. When you do the same process for the energy level distance between n equal 2 and n equal 3, 3 squared is 9, 2 squared is 4, subtract those, you get the coefficient in front of pi squared h bar squared over 2ma squared to be 5. And here's a general expression. If you have two levels, en and en plus 1, the difference between them increases with n like this, 2n plus 1 times pi squared h bar squared over 2ma squared. Next page has a lot of text on it. There's really just one major idea in each of these paragraphs. In this first one, the major idea is that it's the Schrödinger equation that dictates the behavior of these wave functions, because remember what it depends on. That second spatial derivative of psi of x, that represents the curvature of the wave function. And if you look back at equation 4.8 in chapter 4, that's back on page 108, and it says that the curvature is proportional to k squared, and k squared is proportional to energy. Remember, v is equal to 0 in this case. So that says higher energy wave functions must have more curvature. And when you have a sinusoidally oscillating function, more curvature means you'll have more cycles in a given distance. So of course, you expect to see more nodes in the well for higher energies, that is, bigger values of n. Another way to think of that is, since the wave number k is getting bigger, the wavelength is getting shorter. But in addition to satisfying the Schrödinger equation, we said the allowed wave functions have to match the boundary conditions. And the boundary condition we enforced was that the amplitude of the wave function must be 0 at both edges of the potential well. Well, given that it's got to be 0 at both edges, it makes sense that the wave number and the energy can only have certain allowed values, which cause the curvature of the wave function to bring the amplitude exactly back to 0 at both edges. So that's how the Schrödinger equation and the boundary conditions dictate the wave functions that we've just seen. Speaking of these wave functions, a little paragraph here about the fact that you may have seen them before if you've ever studied classical mechanics with standing waves, that is a string, for example, clamped at both ends and oscillating. The so-called normal modes of vibration of that string, if it's a uniform string and it's rigidly clamped at both ends, they will take on wave functions that look like the ones we've just seen. They're even quantized, with each higher frequency mode adding a half cycle along the length of the string. It does point out, however, the analogy is not perfect because string waves obey the classical wave equation, which has second-order spatial and temporal derivatives, whereas the Schrödinger equation, as mentioned in chapter 3, is more like a diffusion equation, the temporal derivative being first order. And that leads to a different dispersion relation. That is, in the classical wave equation, the angular frequency omega is proportional to the wave number k, but in our case, we know that E, which is h bar omega, is proportional to k squared. That's going to have impact on how the wave functions evolve over time, as you'll see a little later in this section. Before we talk about the time evolution of wave functions in the infinite rectangular well, we should talk about probability of measurement outcomes. As it said back in section 3.3, the time-independent Schrödinger equation is an eigenvalue equation for the total energy operator. So the solutions we just got, those psi sub n of x, are the energy eigenfunctions represented in position space. Those values we got for the energy are the corresponding eigenvalues for those eigenfunctions. Knowing that those are the eigenfunctions and eigenvalues, it's fairly straightforward to figure out what are the possible outcomes of energy measurements for a particle in an infinite rectangular well. As it says here, if the particle state happens to correspond to one of the eigenfunctions of the Hamiltonian operator, energy measurement will definitely give you a result that is the eigenvalue associated with that eigenfunction. That is the E sub n that we show in equation 5.7. But what if the state is not one of the energy eigenfunctions? How do we get the expectation value then? Well, if you read through the earlier chapters, you've already seen the math. Remember, we can represent a function psi as a weighted linear combination of eigenfunctions, psi sub n of x, in which c sub n tells you the amount of each of those eigenfunctions present in the mix. Way back in chapter 1, we wrote that using kets, in which the state represented by ket psi is shown as the weighted combination of some amounts, C1, C2, up to C sub n, and eigenkets psi sub n. If you want to know how much of a given eigenfunction is contained within the function psi, use the inner product to project psi onto psi sub n. The integral form of that is shown here, so if you have a function psi that is a combination of eigenfunctions, you can find out how much of each of those eigenfunctions is in psi by taking the complex conjugate of each one, multiplying it by psi, integrating, in this case, over the width of the well. Once you have those c sub n's, now you're able to find the expectation value of energy. Why? Because those c sub n squared determine the probability of each outcome. The possible outcomes are represented by E sub n. The amount of each of the corresponding eigenfunctions is C sub n. So when you take the square magnitude of those C sub n's, multiply it by each eigenvalue and add those up, that's the expectation value for the energy. You can see that in action looking at the problems at the end of this chapter, and the solutions in the app or online will walk you through it if you need help. So that's how you find the energy expectation value. What if you want to know the probable outcomes of position measurements? Well, to do that, we need to know the probability density for position, which we've called Pden of x, and you know that that's related to the wave function psi sub n of x by forming psi star psi. In the case of the eigenfunctions we just derived, here psi star, it's real, so the complex conjugate doesn't do anything. Here psi, when you multiply those together, this is what you get. That's going to be the probability density as a function of x for the eigenfunctions of the infinite potential well. You can see those probability density functions in this figure. As always, when you're confronted with a new figure, it's a good idea to make sure you understand what the axes represent. Notice in this case, although the horizontal axis is labeled x, by the fact that it runs from 0 to 1, you can tell that this is really in units of a, the width of the well. So when x equals 0.5, that's the location of the middle of the well. Likewise, in the vertical axis, it says this is the probability density as a function of x, and in the one-dimensional case, probability density is expressed as probability per unit length. In this case, since the length unit is the width of the well, this is probability per length a, the width of the well. You can see some interesting things in these probability density plots. For the ground state, that is n equals 1, the particle is most likely to be found in the very center of the well, but there is some decreasing probability as you move away from the center of the well of finding the particle anywhere. So position is not quantized in this infinite potential well, although if you look at the excited states, such as the first excited state n equal 2 or the second excited state n equals 3, notice there are locations where you will never find the particle. Those correspond to the nodes of the position wave function, and when you square it, the probability density is 0 at those locations. The other thing to note is that the area under the curve, that is, the probability of finding the particle somewhere in the well, must always be 1. So the area under the ground state curve or under the first excited state curve, that area is 1 in every case. That's described down here, but it also says if you want to find the probability of measuring the particle's position in a specified region, it's necessary to integrate over that region. You can see that better if I clean this up a bit. So for example, if I want to know the probability of finding the particle in the ground state at a location between 1/4 and say 3/4 of the well width, I would have to integrate this function over this range and find this area under the curve. Likewise, if the particle's in the third excited state and I want to know the probability of finding the particle between 0.5 and say 0.9 of the well width, I would integrate over that region, leaving out the little bit on the right, and that integral would give me the probability of finding the particle between 0.5 and 0.9 of the width of the well. Here's what that looks like in equations. You see the limits of integration are from x0, that's the center of the region we're trying to determine the probability for, minus delta x over 2. Delta x is the width of the region we're considering, to x0 plus delta x over 2. We have to integrate psi star psi over that, and we know what those are. Sine of n pi x over a. We plug those in, multiply them together. This is the integral we get. One of the chapter end problems has an example of this. Remember, the full solutions are available if you'd like some help in getting the answer. Then there's a paragraph in which I encourage you to think about the difference between the quantum infinite rectangular well and a classical object trapped in some zero-force region bounded by infinite forces at the walls. You could find that classical particle anywhere in there. It could have zero total energy, that is, it could be at rest. It may be moving with some speed, some constant value of energy. It won't be accelerating because the force is zero within the well. And if you make a position measurement, you're equally likely to find it anywhere. But for the quantum particle, first of all, you will never measure it with zero energy. The ground state energy, E sub 1, is the minimum. And you may find the particle with varying probabilities anywhere in the well. But no matter what the state the particle's in, never is the probability uniform across the well, as it is in the classical case. Furthermore, for all of the excited states, there are one or more locations with zero probability that you'll measure the particle to be there. So as it says here, you definitely should not think of a quantum particle in an infinite rectangular well as a tiny version of a classical object bouncing back and forth between reflecting walls. But you can get some additional insight by thinking about the momentum of the particle. To find the momentum space wave function, phi tilde of p, we know what to do. Take the Fourier transform of psi of x. That looks like this. As you'll see, I've plugged in the normalized wave functions for psi of x, brought the constants out front. Here's the integral we get. It's a bit of a nasty integral, but the way to approach it is either turn this into exponentials using the inverse Euler, or turn this into cosine minus I sine using the Euler relationship. When you do that, you should get that phi tilde of p looks like this. Your version should have the correct h bar square root factor in the numerator here. And when you take phi tilde star phi tilde, you should get this. Again, there will be an h bar in the numerator. That's a little hard to look at, but you can see the results in this figure, in which in the ground state, for n equals 1, the most likely value of the momentum is 0, but there are non-zero probabilities on either side of that for the momentum to have non-zero values. By the way, just as in the case of the position graphs, these horizontal axes have been normalized using the factor pi h bar over a for reasons that you'll see in a minute. Likewise, the probability densities are probability per unit momentum, where this is one momentum unit. This paragraph explains that you shouldn't be too surprised to see the fact that you don't get a precise single value for the momentum even in the ground state, because after all, we know this particle is in the well. Therefore, we have some knowledge of its position. And the Heisenberg uncertainty principle tells us that the uncertainty in position times the uncertainty in momentum must be greater than or equal to h bar over 2. So if you estimate the position uncertainty from the ground state wave function and estimate the momentum uncertainty from the ground state momentum function, you get delta x delta p turns out to be about 0.57 h bar, which does satisfy the Heisenberg uncertainty principle that it be greater than or equal to h bar over 2. Now look at the excited states, that is n greater than 1. As you can see, there are two peaks in these states, one corresponding to positive momentum, particle going one direction, the other with negative momentum corresponding to a particle going in the other direction. Notice that as we go from the ground state to higher and higher states, these peaks of momentum cluster around values of momentum that are approximately n pi h bar over a. And the reason for that is explained here. Those maxima of probability density are approaching plus or minus h bar k sub n. And what are k sub n? Those are the quantized wave numbers for each energy eigenvalue e sub n. Remember this, in the ground state, the eigenfunction has exactly 1/2 cycle across the width of the well. That means that the wavelength of that state is twice the width of the well, since it's got half a cycle in the well width. A full cycle will take 2a, twice the well width. And when you calculate k, in this case k sub 1, as 2 pi over lambda 1, you get pi over a. So if you were to use the de Broglie relation, P is equal to h bar k, you would get h bar pi over a. And as you count up in n, the momentum values tend to cluster around n times that basic momentum unit of h bar pi over a. But of course, as you can see by looking at the graph, that does not mean that the momentum of the ground state is well estimated as h bar pi over a. There's a footnote here that explains what's going on there. I'll clean this up so you can see. This state really does have two peaks within it, if you will, two components. There's one and there's another. One is at minus h bar pi over a, the other is at plus h bar pi over a, but they're so close together that they overlap and produce the function you see here. Once those two peaks get farther apart, as they do even in the first excited state, you can see the individual peaks and the overlap is minimized. But this is one reason you cannot just blindly use P is equal to h bar k for the momentum of a particle in the infinite rectangular potential well. Okay, the final bit for us to talk about is how the particle's wave function evolves over time in an infinite potential well. To do that, we have to look not at the time-independent Schrödinger equation, but at the time-dependent version, and that's shown here. As you can see, we've put back together the space and time dependence, the two functions psi sub n and t of t, so the solutions now look like this. Back in section 3.3, we called these stationary states, that is, the solutions to the time-dependent Schrödinger equation, not because the wave function wasn't changing, but because expectation values and probability density functions do not vary over time. You can see why that's true in this case, because imagine taking psi star psi, this exponential term, when you take the complex conjugate, is going to have a plus I e sub nt over h bar, and when you multiply those together, those terms cancel. So the probability densities that we looked at for position and momentum, those will not change as time passes for a particle in one of these eigenstates. But the situation is very different if a particle in an infinite well is not in an energy eigenstate. It might be in a state, for example, that is a combination of two of the eigenstates, and that combination is not in itself an eigenstate. I've picked the ground state and the first excited state here. Here's the ground state. I've given it an amount called A. Here's the first excited state wave function. I've given that an amount called B. Those are going to help us determine how much of the ground state and how much of the first excited state are present in this state. They're also going to help us normalize. Remember, we found the factor square root of 2 over a for a single eigenfunction, but that's no longer the correct normalizing factor in this case. So one of the cases we're going to look at in this part of this section is if A and B are equal. That is, we've got equal amounts of the ground state and the first excited state. To normalize that, we do our usual approach. We set 1 equal to the integral of psi star psi over all space. Now notice I've written A for the ground state and A for the first excited state because we're saying they're equal. There's psi star, there's psi. When you multiply them together, look at what happens. You get the square magnitude of A out front because that's present in every term. But when you do these multiplies and these multiplies, you get a psi 1 star psi 1, and a psi 1 star psi 2, and a psi 2 star psi 1, and a psi 2 star psi 2. Well, if we plug in our psi 1 and psi 2, that now looks like this. Here's the psi 1 star, here's psi 1, here's psi 1 star, here's psi 2. You can recognize it by the fact that inside the sign, that's the n, that is a 2 here, but also it's got the energy of the first excited state, E sub 2. Here's psi 2 star times psi 1, and here's psi 2 star times psi 2. So if you do those multiplications, that looks like this. You get a sine squared of n equals 1 pi x over a. Last term, you get a sine squared with n equals 2 of pi x over a. And in both those terms, the exponential factors with energy, time, and h bar have canceled. You can see that up here. This, when you take the complex conjugate, will cancel with this. Same thing with these two. But for the so-called cross terms, one's an E1 and one's an E2. And that means these terms don't cancel. So that's why they appear on the second and third term, but not on the first and fourth. In any case, you know that these are orthogonal functions because the eigenfunctions of a Hermitian operator are orthogonal. So these two terms are 0 in any case, but I wanted to point out that these are present when you take psi star psi because we're going to need them in a minute. You also know that this, just as it did in the earlier case we looked at, gives a over 2. So does this one, a over 2. And when you add them together, you get 1 equals square magnitude of capital A times 2 over A times A. That means that A is 1 over the square root of 2. That's our normalization factor. This lets us write our wave functions for the equal amounts case. But before we look at the probability density and how it changes over time for that case, I show you a different case in which I wanted to overload the wave function with a lot more of the ground state and just a small amount of the first excited state. In order to make sure that was normalized, I wanted to make a squared plus b squared, the sum of the magnitudes, equal to 1. So I picked 0.96 for A, and in order to make it normalized, that meant B came out to be 0.28. So first, let's look at the probability densities in that case, and then we'll do the equal amounts case. In this figure 5.7, I show what happens to the position probability density across the well as time passes from 0 to some period capital T, which we'll talk about in just a minute, and we do that in 7 steps. So here we are, 1/7, 2/7, 3/7, all the way. Here's time passing. And look at what happens to the probability density. It starts off shifted left of the center of the well because, remember, we're adding a lot of the ground state, but a small amount of the first excited state. And let's look at that wave function. Here's the ground state wave function, here's the first excited state wave function, and we're adding those together at time t equals 0. Remember, they're both going to shift over time according to that e to the minus I e over h bar times t, but they're going to change at different rates. But at t equals 0, you're adding this to this in the left half, so you're going to get a bigger value. On the right half, this one's negative and this one's positive, so you're going to get a smaller value. And that's exactly what we see here. On the left, the ground state and the first excited state are both positive. They're adding together. On the right, the first excited state is negative. It's pulling down on the ground state wave function. And so this is what you see. But again, they're both oscillating at different rates. So over time, the relative phase between them changes. As you can see, after 1/7 of the period, the peak on the left is reduced a little bit, and the right side is growing a little bit. That's because the first excited state is changing with time faster than the ground state. Here we are at 2/7 of the period, and when we're almost halfway there, it's now the right half that's adding in phase, because the first excited state is now adding constructively to the ground state in that half. And as time passes, the process goes the other way, and after one full period, we're back to where we started. So even this relatively small amount of that first excited state has caused the probability density to shift back and forth in the well. Here's what that composite waveform looks like with the 0.96 factor for A and the 0.28 factor for B. So that's described here, and here is the Planck-Einstein relation relating energy to frequency. So higher energy means higher frequency. That phase variation is important, so we're going to look at the mathematics of it here. You know that the probability density is psi star psi. Again, we're not integrating over any range yet. We're just getting the probability density as a function of position and time. But you can look at the integrands of the 4 terms in the normalization equations we used a minute ago, and you can see there that's the first term involving psi 1 star psi 1. There's the 4th term with psi 2 star psi 2. And here are the 2 cross terms for which the exponentials do not cancel. We're going to just combine these 2 cross terms down here by pulling out these common factors, and that leaves us with this summation of those 2 exponentials. And that, according to the inverse Euler relationship, is equal to 2 times the cosine of E2 minus E1 times t over h bar. So there's the cosine. I put the factor of 2 out front here, and that replaces these 2 terms. So what is this telling you? It's probably easier to see if I clean it up. What it says is we'll have the product of the 2 wave functions, and then as time passes, this cosine term will go from 1 at time t equals 0 through 0 to minus 1, through 0 again, and back up to plus 1. So it's that term that causes the probability densities to vary over time. And if we write it as cosine omega t, you can see that in fact E2 minus E1 over h bar is omega. I've written that down here as omega 2,1 to indicate we're using the E2 state and the E1 state. That looks like this. And what that says is the bigger the difference in energy, the faster the probability density will oscillate. You can actually see the case for the ground state and the first excited state here. Here's what omega 2,1 turns out to be in that case. And if we go back to our equal amounts of ground state and first excited state, here's what that probability density evolution looks like. Now that we have more of that first excited state, we have an even more pronounced peak on the left side, and as time passes, that peak shrinks and the peak on the right side grows as the ground state and first excited state get back in phase with one another on that side. So the rate of oscillation of the combined waveform has not changed because we haven't changed E2 and E1. But due to the greater proportion of the first excited state, you can see the peak is a little narrower and the oscillation occurs over a wider range of x. But after one full period t, the peak has returned back to the left side. Again, that's described in this paragraph, in which it also points out that the period t is just 2 pi over omega 2,1, and since this omega is proportional to the difference in energy between the two states, the bigger that difference and the bigger omega, the shorter the period of oscillation of the probability density. So, a couple of summary statements here. For states of the infinite rectangular well that are made up of weighted combinations of eigenstates, the probability density does vary over time. How much it varies depends on the relative proportion of those two states, and the rate of the variation is determined by the energies of those two states. All right, lots of what we've covered in this section is applicable to more realistic situations, and among those is the finite rectangular potential well. That's the subject of the next section.